Yes. Okay. So now let us move ahead. So this was the things what we have discussed, and expecting that now everybody has understood what has been discussed in the previous lecture, because no question is coming. So let us move ahead, and moving to the last point. What is the remaining point as we discussed in the chapter? That is the port timing diagram for a two-stroke and SI and CI engine. Now here you can see when we discussed wall timing diagram, we said that valve is opening and closing. Walls are opening and closing. So we know that walls are there in a four-stroke engine. Obviously, in a four-stroke engine, there will not be, sorry, in a two-stroke engine, there are no walls used. And so let us now move ahead with the discussion of two-stroke engine. So basically, these things we have discussed earlier, but still once again we'll refresh it. So this is a four-stroke engine constructional details and a two-stroke engine constructional details. We said the walls are there, here the ports are there. So this becomes a very important point from the point of view when we said timing diagram. We called it as a wall timing diagram for a four-stroke engine because walls are there. Timing diagrams are called as port timing diagrams because ports are there instead of walls being used in two-stroke engines. So which ports are there? So here we have an exhaust port. So whenever this is opened or closed, we have a port timing diagram. Similarly, we have a transfer port, okay, which is there for inlet. Bring the mixture, that is suction to happen, and this is the inlet valve which is going to open and close when the pressure inside the crankcase is going to decrease or increase. So these are the constructional details of a two-stroke and a four-stroke engine. So in the four-stroke, when we talk of wall timing diagram, these walls we are talking of, and one spark we are talking of. Here, if it is a CI engine, then instead of a spark, there will be a injector. Here also, if this is a two-stroke SI engine, then there will be a spark, and if it is a CI engine, there will be a injector. And instead of walls, we have ports. So whenever we discuss about the port timing diagram, we will be discussing about when the ports are going to open and close. Okay, so once again, we will refresh the operation of a two-stroke engine. When the piston is moving from top dead center, presently the piston is at top dead center. We can see this at top dead center, okay, over here. And when the piston is at top dead center, what is going to happen? Spark is going to be given. So spark is going to be given, and combustion is going to happen. So the combustion is going to happen over here. And when the combustion happens, the work is going to be produced. So the work is going to be produced. Okay, the join back. So remember, whenever you are joining, I have to minimize and then I have to admit you. That becomes an issue. Okay. So we are talking of operation of a two-stroke engine. When the piston is moving from top dead center to bottom dead center, the spark is given. So the combustion is happening, and when the combustion happens, the piston is being pushed down. So the expansion stroke is there. So the expansion is happening. Piston is moving down. So the piston now move down from here to here, and this port, the exhaust port, is going to be opened or uncovered, and therefore the burnt mixture or burnt products of the combustion are going to flow out. So the exhaust process is going to start. Then we have the suction to happen when it further moves down and the transfer port is open. This is your transfer port. When the transfer port is open, suction is also going to start. Then finally it reaches bottom dead center. So it reaches bottom dead center. Now when the piston is at bottom dead center, suction is going on, exhaust is going on, correct? So both the things are going on, and the piston has reached bottom dead center. So this was when the piston was moving from TDC to BDC. Now in a similar manner, let us discuss what happens when the piston is moving from BDC to TDC. So the piston is moving from BDC. So presently the piston is at BDC, bottom dead center, and it is going to move up. And presently the suction is going on, exhaust is going on. Piston is moving up now, and you can see it is about to cover the transfer port. It has covered the transfer port. Now the suction ends, but still the exhaust is going on. And when the suction ends and the exhaust is going on, further as the piston moves, it ends the suction also, sorry, exhaust also, and effective compression starts from here to here. So suction ends and your piston reaches TDC. So while moving down, the expansion was happening, the exhaust was happening, and the suction was happening. While moving up, to some extent the suction was happening, to some extent the exhaust was happening, and further we have effective compression stroke happening. So this is what happens when the piston moves up and down. Now knowing this much, let us now move towards port timing diagram, because we have seen now that there are ports in the two-stroke engine instead of valves, and this particular ports are opened and closed, and we are talking we are going to talk of a graphical representation of when the ports are going to be opened and closed when the engine is working. And we know a two-stroke engine is going to complete its cycle in only two operations, the two strokes of the piston, not two operations, only two strokes of the piston. And in this particular two strokes, we have to ensure that all the four are going to be four operations are going to be completed. So see, this is the issue, coming late, and then I have to every time minimize. Okay, so we have here port timing diagram. Now here we have here port timing diagram we are talking of. So the operation of a two-stroke engine, construction we discussed. So these things we discussed, and then we discussed about when the BDC to TDC, and now we are moving ahead with the port timing diagram. So this particular graphical representation on which we are going to discuss about when the valves are going to open and close is what we call as a port timing diagram for a two-stroke engine. Since ports are being opened and closed, it is called as port timing diagram. Okay, and we are going to indicate the opening and closing, therefore timing diagrams. And here IVO indicates inlet valve opening. So inlet valve is opened. IVC indicates inlet valve is closed. So here it is IVO, IVC, that is inlet valve is closed. Now here it is exhaust port is open. So exhaust port is open. Then we have exhaust wall. So exhaust valve is closed. So here exhaust valve is closed, or exhaust port is closed. So it should be exhaust port. Then transfer port is open. Transfer port is open, and transfer port is closed. So it should be here PP. Okay. So here there is a mistake. So it should be VBO here. It is written over here exhaust port, but while writing the short form, it has become EBC. It is that is EPC and EP. Sorry, T, instead of here B, it should be P. Here instead of B, it should be P over here. So these are the abbreviations we are going to use for indicating. Now what this indicates? This indicates that there are two strokes. Once the piston is moving down from TDC to BDC, and from BDC to TDC second stroke. So in the two strokes, completes the cycle is going to be complete. Therefore, this graphical representation has only one circle. Unlike previously when we discussed about a four-stroke engine, we had two, correct? Two circles. By two circles, we have to represent the four strokes. And in order to represent four strokes, we use two circles. So in some manner we were representing two circles in which four strokes were there, and we discussed what is happening. So again here, if you want to go for theoretically, then the theoretically it is a different to some extent, but we'll directly go for practically what is happening over here. So here, first thing what you have to understand here is this inlet wall opening and inlet wall closing. Now, what is this inlet wall opening and inlet wall closing? So, in order to understand the inlet wall opening and inlet wall closing, here, this is your inlet wall. Now, this wall is opening and closing when this will open, when here we have a wall, and as we discussed earlier, this is a reed type of wall. Reed type of wall means there will be one opening and there will be one flap. You can call it as a flap, or you can call it a reed. Okay, the flap or reed is closing this particular opening. When you can assume that here this particular wall is attached and the reed or flap is on this side. So when the pressure on this side is more, what will happen? The pressure will act on that particular reed or flap and it will be pushed towards the hole. That means the hole is going to be closed tightly. And whenever on this side the pressure is less, it will not be pushed more. Rather, the pressure on this side of the wall from that is atmospheric pressure, it will be more, and pressure on this side is going to be lesser. Therefore, what will happen? It will bend towards this side and it will allow the things to come in. Okay, so that is how it is opening and closing. So there will be a reed wall over here, and that particular reed wall is going to open and close as in when the pressure responding to the pressure inside the crankcase. So when the pressure on this side is increasing, it will press, and when the pressure on this side is decreasing, it will open. So that particular opening and closing. So when this will the pressure will decrease when this moves up. Correct. That is when the piston is moving towards top dead center and it is about to reach top dead center. Here negative pressure has been created, resulting in the opening. Correct. And when this is moving down, so when this has moved up, what happens? The mixture comes in. And when this starts moving down, initially slowly the pressure builds up and the pressure outside and inside becomes equal, and when the pressure inside becomes more than the outside, then the reed will be pressed and further the pressure start building over here. Pressure start building over here. So that means when the piston is moving up, this is going to be open, and when the piston is moving down, this is going to be closed. So that is what we have already indicated over here. So this we can clearly see. We have here inlet wall is opening over here when the piston is moving up. So from BDC to TDC, it was opening, and when the inlet wall is going to close, when the piston is moving down. So here some angles are given. That is before the 50 degrees before the top dead center, the inlet wall is going to open, and after 50 degrees after TDC, the inlet wall is going to close. So this inlet wall is going to remain open for 50 plus 50, that is 100 degree of the crankshaft rotation. So out of 360, about 100 degrees crank angle, the inlet wall is going to remain open, and that time the fresh mixture will be coming from the carburetor into the crankcase of the engine. Okay, so that is about the inlet wall opening. Now we will discuss exhaust port opening and closing and transfer port opening and closing. So let us move ahead. So basically this is your port timing diagram, what you are going to learn, and this is for a two-stroke engine. So initially let us consider that piston is moving from top dead center to bottom dead center. So when that piston is moving from top dead center to bottom dead center, means it is going to move like this in a crankwise manner, clockwise manner. So initially the piston is at top dead center, and we know that just before the piston reaching top dead center, from the previous cycle, the piston has moved up and the effective compression stroke has happened, and therefore just before the piston reaches top dead center, the spark has happened. So ignition is happening over here, some 20 degrees, as which we have discussed earlier also. Being SI engine, we are talking of a ignition or spark over here. So spark has been given and therefore combustion happens. So this is a time corresponding to when the combustion is supposed to happen and still the piston is moving upward and it reaches top dead center. Okay, so the spark is given and your piston reaches top dead center. Now once it reaches top dead center, it has to move down now. So that is where we are going to discuss now. So it is going to move down. So as it is moving down, initially obviously on the lower side of the piston, inlet valve is going to open, sorry, close, because it has opened here, it is going to close over here. That we are not considering now. Here we are concentrating on the upper part of the piston. So on the upper part of the piston piston was earlier here and now it has moved down and the exhaust valve, exhaust port is open. So the exhaust port is open at what degrees? So it is around 60 degrees before the bottom dead center. The exhaust port is open. So as it opens, what happens? The mixture burnt gases over here is going to flow out. Okay, it starts flowing out. That means exhaust gases are flowing out, which as already in one of the lectures we have discussed, this is what we call as scavenging. So here it is written scavenging. It can be also written as exhaust. Okay, so scavenging is going to happen. So here, so the arrows somewhat mistake, I think. Okay, it doesn't matter. So here the exhaust port is open, and here at this particular point, now your exhaust starts. So exhaust starts from here and it continues till it is going to be closed. Okay, so now here exhaust has started. Further, what happens as it further moves down? The inlet port is going to open. The suction is going to happen when the transfer port is opening. So when the transfer port is opening, this is happening around some degrees before TDC, which is 60 degree. So this was 70 degree and this is around 60 degree. So some 60 degrees before bottom dead center, your suction is also starting. So correspondingly now the exhaust is going on and the suction is going on, and further the piston moves down and reaches bottom dead center. Okay, so we were discussing from what is going to happen when the piston is moving from TDC to BDC. So initially it was at TDC, and before TDC ignition has happened and therefore combustion happened. Piston reached TDC, and as it reached TDC, it started moving down. As it started moving down, some degrees, that is around 70 degree before bottom dead center. So 70 degree it is written over here. The exhaust port is going to open. So the exhaust is open, you can see over here, and the exhaust gas is started moving out. Further, the piston moves down and transfer port is also open, which is opened at around 60 degrees from the bottom dead center, before bottom dead center. So the suction also started, and finally the piston reached the bottom dead center. So this is what is happening when the piston is moving down, and correspondingly we have discussed on this side what is happening. So started from ignition, then the piston reached the TDC, then exhaust port opened, then transfer port opened, and piston reached BDC, bottom dead center. Now further the piston will move upward from BDC to TDC. So now we are going to discuss about what is going to happen when the piston is moving from bottom dead center to top dead center. So now the piston is initially at TDC, bottom dead center, BDC, and it is going to move up. So it is going to move up. Now further as it moves up, initially it closes the transfer port. So initially you can see over here the transfer port is closed now. So here the suction was happening, the exhaust was happening, but here the suction stops. Only exhaust is still happening when the transfer port is closed, because transfer port is closed over here, therefore nothing can come in through the transfer port. Okay, now further it is going to move up, and as it moves up, here the exhaust port also closes. So exhaust port also closed now. So here both was open. Here the transfer port closed. Here the exhaust port also closed. And further, as it moves up, and at a certain some degrees, around 20 degrees before top dead center, the ignition happened and the combustion is going to happen, and finally the piston is going to reach top dead center. Okay, so the finally piston is reaching top dead center, and as discussed earlier, the same thing will repeated whatever we have discussed in the previous slide. Okay, what is going to happen when the piston is moving from bottom dead center to top center? Initially it was at bottom dead center, suction was happening, exhaust was happening. It moved up, transfer port closed. So when the transfer port closed, suction ended. Then it moved up, exhaust port also closed. So what happened? Now exhaust also ended, and effective compression started, and after some 20 degrees before top dead center, the ignition of the spark is going to be ignited, and the combustion starts, and further the piston moves up and finally reaches top dead center. So this is what is indicated on this particular port timing diagram. So I think the things are clear now. So here that is what is discussed over here in this port timing diagram. So a port timing diagram is nothing but a graphical representation of which ports are going to open and closed in a two-stroke engine. Okay, in a two-stroke engine, because the two-stroke engines used ports instead of valves. So the ports are going to be opened and closed. So initially we discussed about the inlet valve opening and inlet valve closing. So the inlet valve is opening when the piston is moving up, and inlet valve is closing when the piston is moving down. Okay, so when it is moving up, this was opening, and when this is moving down from TDC, this is closing. Okay, and further we discussed about what is happening when the piston is moving from TDC to BDC. So initially, as is it nearest to the TDC, ignition was happening. So due to ignition, the combustion was happening. The combustion increased the pressure. Piston reached the top dead center. Now the combustion is going to complete, and the pressure is going to act on the piston, and the piston starts moving down. So that is what we discussed in the previous slide. That is here we said as the piston moves down, initially the exhaust port was opened, and the mixture, burnt mixture inside the combustion chamber starts moving out. Further it moved down. So here you can see the exhaust has started. Further piston moved down, suction has started. Further it moved down and reached the bottom dead center. So this was what is happening when the piston is moving down. And further in this slide we discussed what is happening when the piston is moving up. So here suction was going on, the exhaust was going on. Here the suction ended, but still the exhaust is going on. Here the exhaust also ended, and finally piston was about to reach TDC. At that time, some 20 degree before that, ignition took place, and due to ignition, combustion started, and finally piston reaches top dead center. Okay, so this is what is port timing diagram. So now before discussing further, can I know is there any doubt related to port timing diagram? Anybody having? Please unmute yourself if you have any doubt in port timing diagram. Anybody having any doubt? Please unmute yourself. Unmute yourself, please, and let me know if you have any doubts. Anybody? Anybody having any doubt? Suhas Naste, any doubt?
Yes, sir.
Any doubt?
फोर स्ट्रोक म्हणजे जसं प्रॅक्टिकल आणि थेरॉटिकल असते तसं असते.
हा, इथं थेरॉटिकल आणि प्रॅक्टिकल काही वेगळं आहे का? नाही, कारण काय की थोडासा फरक असतो, परंतु इट इज नॉट दॅट मच to the extent that it can be converted into two diagrams. Karan काय की the design of these particular things are coming into picture due to design itself. In the ideal four-stroke, that is theoretical four-stroke cycle, we assumed that the walls are opening and closing at top dead center. Okay, in a two-stroke engine, can we assume that the ports are going to open at the top dead center and bottom dead center?
No.
Suhas?
Yes, sir.
Can we assume? Can we assume? No. Correct. Because see, if you see the diagram of a two-stroke engine, then you can clearly say that you cannot assume that it is going to happen. So here you can see this wall may, this port may be to some extent upper side, but it cannot be at a top dead center. Correct. This port cannot be at bottom dead center. So theoretically, even theoretically, we cannot assume that this exhaust is going. See, if this is at a top dead center, what will happen? Obviously, this combustion will not happen. Correct. So this has to be on the lower side. So since it is being assumed that it is wherever it is, ते जिथं आहे तिथंच ते आपण थेरॉटिकली पण अज्युम करतोय, म्हणून याला थेरॉटिकल वेगळं डायग्राम आणि प्रॅक्टिकल वेगळं डायग्राम येत नाही फोर टायमिंग डायग्रामला. बट इन अ फोर स्ट्रोक इंजिन व्हॉट इज हॅपनिंग? इन अ फोर स्ट्रोक इंजिन वी आर अज्युमिंग दॅट थेरॉटिकली इट वॉज सपोज टू बी हॅपन ऍट टॉप डेड सेंटर. म्हणजे थेरॉटिकली आपल्याला ती टॉप डेड सेंटरला व्हायला अपेक्षित आहे. का? पोर्ट जर तुमचं वॉल टॉप डेड सेंटरला ओपन केलं तर सक्शन तिथं स्टार्ट झालं आणि सक्शन पिस्टन टॉप डेड सेंटर पासून बॉटम डेड सेंटर येईपर्यंत सक्शन होते असं आपण थेरॉटिकली अज्युम करतोय. मग आपण एकदा बॉटम डेड सेंटरला आलं की वी आर अज्युमिंग दॅट इट इज गोइंग टू क्लोज. बट ड्यू टू सम इनहेरेंट डिझाइन features in the cam and follower mechanism, okay, you cannot practically go for that. Okay, and if you do that, then what is going to happen? It is going to affect volumetric efficiency, which we have already discussed. Okay, but here you cannot see इथं जर आपल्याला जर पोर्ट ओपनिंग जर इथं टीडीसी ला करायचं असेल तर इथं कंबशन होईल का? सुहास नाही. हा, कंबशन होणारच नाही, कारण कंबशन इथं होत आहे आणि इथंच आपण जर एक्झॉस्ट पोर्ट लावला तर इथं कंबशनच होणार नाही, कारण इथं ओपनिंग असल्यामुळं इथं किती जरी तुम्ही प्रेशर लावला तर ती सगळ्या गॅसेस इथून बाहेर जातील. बरोबर. सो here you cannot assume that the ports are at top dead center and bottom dead center even theoretically, and therefore we don't have a theoretical port timing diagram and practical port timing diagram, even though there will be some changes, very small changes, negligible amount of changes. Okay, now anybody else having any Sainath Kharade, unmute yourself. Sainath, I think Sainath has been sleeping. Sainath Kharade, in the previous lecture also I asked Sainath some question and he left. Sainath is not responding, so I will mark Sainath Kharade absent. May I mark Sainath Kharade absent? Okay, Rohan Bandare. Can Rohan Bandare unmute yourself? Rohan Bandare.
Yes, sir.
Please. Any doubt?
No, sir.
No. Then if you say no, then I will ask you a question. Should I? विचारू का? Yes. विचारू का? Okay. Tell me, Rohan Bandare, why or how the inlet wall is opening and closing in a two-stroke engine? Rohan Bandare. how the inlet valve is opening and closing in a two-stroke engine? Unmute yourself. Unmute yourself and give the answer. Rohan Mandare.
Yes, sir.
Yes. Give me the answer of the question. How the inlet valve is opening and closing in a two-stroke engine? Yes. Don't know? Rohan? Rohan? Do you know or you don't know?
Don't know, sir.
Don't know. Then you said you understood everything. Vijay Surve. Vijay Surve, can you unmute yourself?
Yes, sir.
Please give the answer of the question. How the inlet valve is opening and closing in a two-stroke engine?
No, sir.
Why no?
Clearly.
When I'm asked, please.
Clearly.
Bola. Clearly. What? You are not understood.
I am not understood.
You are not understood. Then why you are not asked the question? Okay, Swapnil Ubale. Okay, mute yourself, no problem. Swapnil Ubale. So, tell me the answer of the question. How the inlet valve is opening and closing in a two-stroke engine? Please. Inlet valve is opening and closing. How? Swapnil Ubale. Please speak. Swapnil Ubale. Please. Swapnil Ubale. Okay, anybody? Can anybody answer? From the class answer. How the inlet valve is opening and closing in a two-stroke engine?
Sir, in the engine, the valve timing is the precise timing.
Okay.
And in that, it can be varied by modifying the camshaft also.
Okay. Now, my question is very precise. Are you able to see on the screen now?
Yes, sir.
Okay. This is the inlet valve.
Yes, sir.
Okay. And the question is how this particular inlet valve is opening and closing. That is the question.
Sir, when the piston moves towards the bottom dead center.
Towards the bottom dead center. Okay. From top dead center. Okay.
Yeah. Then suction is created in the cylinder.
In the cylinder. Okay.
So this makes the inlet valve to open, and it is placed like a strip on the valve.
See, you are talking of this particular piston moving down, correct?
Yes, sir.
And the suction is happening over here, correct?
Yes, sir.
Now, how the suction over here make this particular valve to open?
Sir, when this piston will move towards upside the spark plug, so there will be suction created in the inlet valve, no, sir, downside.
Okay, now we are talking of piston moving upwards.
Yes, sir.
Okay, when the piston is moving from bottom dead center to top dead center, what is happening? What is happening?
There is suction created in the lower part of the crankcase.
Okay. Okay, very good. So negative pressure created in the sump. Okay.
Yeah, and when the piston moves from the bottom dead center to the top dead center, there is pressure created, which makes the exhaust port to open.
Exhaust port to open. Here, this. But we are talking of this closing, opening and closing of this.
Sir, when it comes down to the bottom dead center, there is pressure when it moves to the top dead center, there is suction created, and that lets the inlet valve to open.
Okay. And closing. Closing. Okay. Thank you. Anybody else can answer? Anybody voluntarily? Instead of asking the names, please.
When the piston is at top dead center, the inlet valve is already opened.
Opened.
Already is
Okay.
open condition and suction is going on. When piston is move from top dead center to bottom dead center, then the pressure is applied on the wall and wall gets closed. When it reaches bottom dead center, it is completely closed, and then when it moves from bottom dead center to top dead center, then the pressure go on decreasing, and due to decreasing pressure, the wall is opened and the suction is taken.
Okay. So this was Suhas Naste.
Yes, sir.
Okay. Very good, Suhas. So right answer he has given. Okay. So how it is opening and closing? Due to the negative pressure or the positive pressure created in the sump. And this negative and positive pressure created in the sump is due to the piston motion. So when the piston moves up, म्हणजे ज्या वेळेला piston वरती जाते त्यावेळेला suction. Here the negative pressure is created. So whenever the pressure inside the sump is more than the outside, here it is atmospheric. So when the atmospheric pressure is more than this, at that time it has to flow. Okay, and that will be done when the piston is moving up. And when the piston is moving down, a positive pressure will be created, and at that time this will be closed. Okay, and this will be closed, and still this will continue to move down. At that time this will open, and have the positive pressure make this to flow like this, and it is coming down. ओके, हे ज्या वेळेला पूर्णपणे खाली येईल त्यावेळेला इथं पॉझिटिव्ह प्रेशर क्रिएट झालेलं आहे आणि हे ओपन झालं की देन द गॅसेस विल फ्लो इनटू द कंबशन चेंबर. ओके, सो दिस इज हाउ द इनलेट वॉल्व इज ओपनिंग अँड क्लोजिंग. So I hope everybody understood the pore timing diagram. Yes. Can I assume that everybody has understood?
Sir, hello.
Please. Balaji Pise, please.
सर एक प्रश्न आहे.
प्रश्न विचारा.
सर जेव्हा पिस्टन बीडीसी टू टीडीसी ला जातो,
बीडीसी कडून टीडीसी कडे चाललोय, बरं.
त्यावेळेस इनलेट वॉल्व पेक्षा टोटल सायकल मध्ये इनलेट वॉल्व पेक्षा एक्झॉस्ट वॉल्वचं टायमिंग जास्त आहे.
इनलेट वॉल्व पेक्षा
एक्झॉस्ट वॉल्वचं टायमिंग जास्त आहे. तर तेवढा प्रेशर पुरेसा आहे का म्हणतोय मी? कमी 30 to 40% टाइम
नाही. एक मिनिट ठेवा. ही जी ओपनिंग आणि क्लोजिंग होते इनलेट वॉल्वचं, ही दिसतं इथं. दिस इज हॅपनिंग ऑन द बॉटम साइड ऑफ द पिस्टन, आणि इथं जी दाखवलंय दिस इज हॅपनिंग ऑन द अप्पर साइड ऑफ द पिस्टन. इज इट क्लिअर?
हा बरोबर आहे सर, पण ज्या वेळेस पिस्टन बीडीसी टू टीडीसी चाललेला असतो त्यावेळेस
इथं दिसतंय की बीडीसी टू टीडीसी ला चाललाय.
एक्झॉस्ट वॉल्व सुद्धा ओपन असतो त्या टायमिंगला.
एक्झॉस्ट वॉल्व सुद्धा ओपनिंग, पहिल्यांदा एक्झॉस्ट म्हणजे पहिल्यांदा इनलेट वॉल्व क्लोज झाला, सॉरी ट्रान्सफर पोर्ट क्लोज झाला, त्यानंतर एक्झॉस्ट पोर्ट पण क्लोज झाला. पुढे
पण त्यावेळेस प्रेशर खालून असं जाताना बघा, हे 70 डिग्री दाखवलाय अँगल.
70 डिग्री.
मग 7 डिग्री म्हणजे मिनिमम 30% तर त्यानं हे सोडलं बाहेर, गॅस सोडला.
नाही. बरं. तुम्ही आता इनलेट मधला आणि एक्झॉस्ट मधला डिफरन्स बद्दल बोलताय का?
त्या सिलेंडर मधला त्याने गॅस किती बाहेर सोडला ते बोलतोय मी. म्हणजे त्यावेळेस
म्हणजे आत किती येतोय बाहेर किती जातो ह्याच्याबद्दल बोलताय का तुम्ही? इथला हे आत येणार आणि हा बाहेर जाणारा, बरोबर?
एक्झॉस्ट वॉल्व ओपन असेल त्यावेळेस प्रेशर काय नसणार आहे त्यावेळेस.
बरोबर. करेक्ट.
पिस्टन वर जाताना प्रेशर कमीच क्रिएट होणार आहे म्हणतोय ना.
बरोबर आहे.
मग त्याचा काही इफेक्ट होणार नाही.
मग तेच आता बघा ठेवा. ओके, आय विल एक्सप्लेन दिस पर्टिक्युलर थिंग. सो हिअर इनिशियली यू कॅन सी द एक्झॉस्ट, म्हणजे इथं एक्झॉस्ट ओपन झालं, बरोबर. अजून खाली आलं इनलेट ट्रान्सफर पोर्ट पण ओपन झालं. आता ही ट्रान्सफर पोर्ट मध्ये येणारे गॅस, व्हॉट इट इज डुईंग, इट इज पुशिंग द गॅसेस ओव्हर हिअर See, that is why this particular provision of this particular upper side, you can see something bump like feature that is given. हे कशासाठी दिले? हे जर ही नसतं तर काय झालं असतं? हे गॅसेस असे सरळ फ्लो झाले असते. पण आपण काय केलं? इथे एक एक्सटेन्शन दिलं. आता याला काय केलं? सो दिस पर्टिक्युलर गॅसेस आर डिफ्लेक्टेड टुवर्ड्स अपवर्ड साइड. ओके, आणि दिस पर्टिक्युलर डिफ्लेक्टेड गॅसेस काय करतायत? इथं ऑलरेडी इथं प्रेझेंट असलेल्या त्या एक्झॉस्ट गॅसेसला बाहेर ढकलतायत. Okay, and this particular process is called as scavenging. Now, earlier lecture, one of the lecture we have discussed about scavenging. So this is what scavenging is. Okay, the scavenging is flushing out the exhaust gases from the cylinder is called as scavenging. Scavenging is going to happen. आता तुमचा प्रश्न हा आहे की हे 70 आणि 70 म्हणजे 140 झालं आणि हे 60 आणि 60 म्हणजे 120 झालं. हे तुमचा प्रश्न आहे का? हॅलो
तर तसं नाही, मी म्हणतोय एक्झॉस्ट वाल्व ओपन राहणार आहे.
हा, एक्झॉस्ट वॉल तर ओपनच आहे.
ओपन आहे एक्झॉस्ट वाल्व. 70% दाखवलंय फ्रॉम बीडीसी पासून वर जाताना.
बरोबर. हा, ठीक.
मग त्या टायमिंगला एक्झॉस्ट वाल्व ओपन राहिल्यामुळे प्रेशर आत कमी असणार आहे त्या टाइम.
बरोबर आहे.
जेव्हापासून एक्झॉस्ट वाल्व बंद होईल तेव्हापासून प्रेशर क्रिएट होणार आहे.
करेक्ट, बरोबर, एकदम बरोबर.
हा, आणि मग त्या टाइमिंगला प्रेशर कमी क्रिएट होतोय असं मी म्हणतोय. एक्झॉस्ट वाल्व 70% जास्त वेळ राहिल्यामुळे.
येस, आय गॉट द क्वेश्चन. सो क्वेश्चन इज आपण ही गोष्ट ज्या वेळेला 2 स्ट्रोक आणि 4 स्ट्रोक डिस्कस केली त्यावेळेला डिस्कस केलं. आपण म्हणलं होतं की इथून पुढं दिस इज द इफेक्टिव्ह कॉम्प्रेशन स्ट्रोक. इथपर्यंत पिस्टन इथून इथपर्यंत आला, काहीही कॉम्प्रेशन झालेलं नाहीये, कॉम्प्रेशनच झालेलं नाहीये सिलेंडर मध्ये. हे खालनं आला वरती आला, परंतु इथपर्यंत येईपर्यंत काहीही कॉम्प्रेशन झालं. देयर इज नो कॉम्प्रेशन हॅपनिंग. Once the exhaust port is open, thereafter we say from here to top dead center, this is your effective compression stroke. म्हणजे ही बॉटम डेड सेंटर म्हणजे बीडीसी इथून आहे, इथून इथपर्यंत हा स्ट्रोक आपला असायला पाहिजे होता, परंतु कॉम्प्रेशन स्ट्रोक कुठून आहे? इथून इथपर्यंत फक्त आहे, म्हणजे या पोझिशन पासून या पोझिशन पर्यंत एवढाच कॉम्प्रेशन स्ट्रोक आहे. सो द इफेक्टिव्ह कॉम्प्रेशन स्ट्रोक इज व्हेरी व्हेरी लेस इन 2 स्ट्रोक इंजिन. आणि म्हणून आपण ज्यावेळेला कम्पेअर केलं त्यावेळेलाच आपण म्हटलं होतं की ड्यू टू लेस इफेक्टिव्ह कॉम्प्रेशन स्ट्रोक द वर्क प्रोड्यूस्ड इन अ 2 स्ट्रोक इंजिन इज लेसर दॅन 4 स्ट्रोक इंजिन एफिशियन्सी. तुमचं म्हणणं एकदम बरोबर आहे. व्हॉट एव्हर सेइंग इज व्हेरी राईट. दॅट इज द इफेक्ट कॉम्प्रेशन स्ट्रोक. इथं तुम्ही ही पिस्टन ज्या वेळेला वरती मोहतात असताना देर इज नो कॉम्प्रेशन बिईंग प्रोड्युस्ड. इथनं वरती झालं, इट रीच्ड अप टू हिअर, until it reaches this particular position there is no compression. इथून पुढे ज्या वेळेला पिस्टन मूव्ह होईल, then and then only the piston is going to have compression. I hope you are clear.
Yes sir.
Point is
clear.
Okay.
Clear.
Okay. Anything else? Anybody having any doubt? Please ask. See, then I will start asking question. Prathamesh Kottukond, please unmute yourself. Prathamesh, please tell me this how the what is the amount of expansion stroke, power stroke in a 2 stroke engine when compared to that of a 4 stroke engine. 4 stroke आणि 2 stroke मध्ये कंपेअर केलं तर पॉवर स्ट्रोक किंवा एक्सपान्शन स्ट्रोक किती आहे? दॅट इज द क्वेश्चन. प्रथमेश, आन्सर. प्रथमेश, प्लीज स्पीक. प्रथमेश कोटगोंड, प्लीज स्पीक.
हॅलो. 4 स्ट्रोक इंजिनचं सर एक्सपान्शन जास्त आहे 2 स्ट्रोक पेक्षा.
हा, आणि 2 स्ट्रोकचं
कमी आहे सर 4 स्ट्रोक पेक्षा.
का कमी आहे?
सर त्याचं
येस
हॅलो.
येस. हा, का कमी आहे प्रथमेश? का कमी आहे? वाय यू आर अनम्युटेड. हा, का कमी आहे म्हणून मी विचारतोय.
नाही. हॅलो.
कमी आहे, बरोबर आहे हो तुमचं, परंतु का कमी आहे प्रथमेश? येस, आय कॅन हिअर
नाही
यू,
सर.
प्लीज स्पीक. हा,
समजलं नाही सर.
समजलं नाही. See, when I am asking the question, you are telling me you are not understood. Then why you are not asking the doubt then? Huh? So is it necessary that every time I have to ask the question and make you remind me about your why whether you are understood or not? Huh? Okay.
हा सर.
Here see from TDC to BDC. आता इथून काय आहे की ही पहिल्यांदा TDC पोझिशन आहे. इथून इथपर्यंत इफेक्टिव्ह एक्सपान्शन स्ट्रोक आहे. इथून पुढे आलं की the exhaust gases are leaked out. So there is no further power acting on the piston. कारण ह्या प्रेशर जे आहे ती लीक झालं. Since the pressure has been leaked out through the exhaust, there is no further pressure acting on the piston and therefore no power stroke. So effective power stroke is from TDC to this particular piston when it is reaches over here, and this is just to open. त्यावेळेलाच फक्त म्हणजे एवढाच फक्त पॉवर स्ट्रोक आहे. परंतु फोर स्ट्रोक इंजिन मध्ये कुठे आहे? TDC पासून BDC पर्यंत. And therefore the effective power stroke is more in a four stroke engine and less in two stroke engine. Why it is less? Because of the arrangement of the port. We are using ports and the port is arranged over here. So whenever it is going to move down from this particular position, your power stroke is going to end. Correct? Prathamesh? Understood?
हा सर. Yes sir.
Okay. Any other doubt? Anybody having any other doubt? Yes. Okay. So now moving to the last bit of the last point, that is for SI and CI engines, the port timing diagram is shown here. So here you can see the port timing diagram for a SI engine, that is a petrol engine. So here the inlet valve closed, opened, inlet valve closed, the exhaust port opened, the exhaust transfer port opened, the transfer port closed, exhaust port closed, and this is what we have discussed now. And here there was some degrees before TDC. So in the last slide we have seen it was 20 degrees. So there was ignition happening. Okay, and instead of this is the port timing diagram for a petrol engine. And for a diesel engine, then what is going to change? Here we had sucked the mixture through the intake valve, inlet valve into the crankcase first, and from the crankcase through transfer port, it has been delivered to the combustion chamber in case of petrol engine. Now the same path is followed over here, but what is being sucked is only air. Only air. So here inlet valve opens, inlet valve closes. Correct? And that is where the mixture is coming in. Now here not necessarily, because we can use this particular also for diesel engines also, but only air is going to come. And when the piston is reaching TDC, nearer to TDC, your injection starts, and the injection is happening over a period of 20 to 25 degrees fuel supply. So here the point of injection, and the injection is going to end over here. Fuel injection starts, fuel injection is completed. So here it was the ignition starting or combustion starting, and somewhere here the combustion ending. Okay, but we are only denoting here the injection, the spark point. Okay, so or in the ignition point. So the ignition starts over here or the combustion starts over here. Here the fuel injection starts, and the fuel injection is not instantaneous. It will happen over a period of time. थोडंसं ती स्टार्ट झालं, it will go on spraying for some amount of time and then it is completed. Okay, so by the time piston has reached TDC and then coming down. So this around 25 degrees during this particular 25 degrees of crank rotation, the fuel was supposed to supply, and this becomes the difference between a port timing for a petrol engine or SI engine and a CI engine. Okay, so all the things remains almost same, all the same, because the port, whenever the port is open, the exhaust port is open, the exhaust is going up. When the transfer port is open, the mixture is or air is coming in, whatever is okay. All the other things, the lower part remains the same here and here. Okay, the only the upper part there is small change. What is the change? Here it is the ignition point. Here is the fuel injection starting and fuel injection ending. So that becomes the difference between a port timing diagram for a SI and CI engine. I hope everybody has understood the difference between a port timing diagram for a SI and CI engine. Any doubt? Only changes here you have to indicate the spark point, while here you will indicate the start of injection and end of injection or completion of injection. Okay, fuel injection starts, fuel injection completed. Okay, denoted by FISO here. So this yellow point is the fuel injection starting point, and this is the fuel injection completion point, and this is the this green range, whatever has been shown over here. This is your fuel injection point. Now here you can see this red one was your expansion stroke. Here also the red one was expansion stroke. Expansion stroke was up to when the exhaust port is opened. आपण बघितलं एक्झॉस्ट पोर्ट ओपन झाले की तिथून पुढे एक्सपान्शन होत नाही असं म्हणतोय आपण. काय एक्सपान्शन होत नाहीये? कारण pressure has been leaked. Okay, so here the expansion end, and you can see when the exhaust port is closed, when the piston is moving up, तिथून पुढे आपण काय म्हणतोय, compression start over here and compression ended over here. Compression started over here, compression ended over here. Expansion started over here, expansion ended over here. So compression, expansion, and the ports opening, closing, same. So everything remaining the same. What is the difference between the SI port timing diagram and the CI port timing diagram? It is the point at which the spark is given is being replaced by the point of starting of the injection and ending of the injection, fuel injection. Okay, so I hope you have understood the difference between the port timing diagram for SI and CI engine. So this again is going to be the next question for your so I will write the question number 3 for your assignment. So the question is, with a neat sketch, explain the port timing diagrams for SI and CI engines. So with a neat sketch, explain the port timing diagram for SI and CI engine. I think the question is now available in the chart. Sir, please show some video to clear all concept about two-stroke engine and four-stroke engines. Say the showing the videos. See, there is no problem in showing the videos, but I don't know whether you will be able to hear the sound or not. So it is not a big issue for me to show the videos of okay, I will try to show, but check me, tell me whether you are able to see the Is my screen visible now? Can anybody confirm?
Yes, sir. Yes, sir.
Can anybody?
Yes, sir.
Okay.
Sir.
So video is seen? Okay.
Yes, sir.
So this is can you tell me whether video is able to see and its voice was able to be heard? Shubham? Shubham? Anybody?
Sir, video is seen, but voice is not coming.
Correct. So that is the problem. That is the reason why I was not showing the videos. Okay, that means what happens is simultaneously I have to show the video and I have to. So at least you understood now how a petrol engine works. So here Rishikesh Deshmukh has said some videos has to be shown. So I will try to show the videos. So this is a engine and its construction details are seen on over here. So this is a engine block. You can see the cylinders. This is your crankcase, which is on the crankshaft on the bottom side. and here we have the supports for the crankshaft. So the crankshaft is rotated. This is actually the bottom side of the engine. Okay, and these are the cranks. You can see the crank weights. These are the supports we are talked of. Okay, these now we have connected the connecting rods. So you can see the number of connecting rods connected, and on the opposite side of this connecting rods, sorry, on the other end of the connecting rod, we have connected the pistons. Now the walls have been connected, and the camshaft is going to drive this particular walls. This camshaft is driven by the crankshaft. So the camshaft drives the walls, and camshaft is driven by this particular chain with the help of a crankshaft. And this is a sump which is on the lower side where the lubricating oil is going to be there. This is the oil filter to filter the oil before it can be sent to the engine, because every time it goes and comes back, it has to be filtered. This is your rocker mechanism which is going to operate the valves. So whenever this particular rocker operates, the valves are going to be operated. These are the rocker covers, and these are the manifolds. So the inlet and exhaust manifolds are there. So the inlet and exhaust manifolds allows the inlet air to go in, and exhaust manifolds allow the the exhaust gases to come out. This is a throttle arrangement for allowing the accelerator. So when the accelerator is given, this throttle is going to open and air is allowed to go in. So this is for inlet manifold. This is a pulley for connecting this particular pump, water pump, etc., which is there for the cooling system. On this side we have, so here we have this exhaust system, and this is your intake system. So the intake manifold and exhaust manifolds here. Okay, so that is the arrangement. Here we have an alternator. So this is about the constructional details of an engine. So with the help of a pulley, you are putting this water pump is there. So this will be there for the cooling system. This is the alternator to produce the electricity for ignition system. Okay, so this was the constructional details of an engine. Then we have one more. So this is how the engine is operating is shown over here. So you can clearly see the pulley rotating, which is this pulley is connected to the crankshaft. So this is your crankshaft rotating. Correspondingly, the pistons are moving. The valves are being operated by the camshafts over here. The camshafts are run by the crankshaft. Okay, so this is the actual operation, how it is happening inside engine, and how the valves are being opened and closed. So you can see over here the valves are opened by closed. This is your cam and this is your follower. So whenever the inlet valve opens, the mixture comes in, the spark is over here, spark is given, that it is burned. So it is burning now, and the exhaust gases are flowing. So the blue one, what is seen is the mixture coming in, and the red one is shown as the exhaust gases flowing out. Here the injector is shown. The injection happens when the piston is at almost top dead center. The injection is happening. So it is now a diesel engine instead of a spark ignition engine, CI engine, because the diesel was sprayed. So this is a cylinder block. These are the cylindrical holes. This is your crankshaft. These are connecting rods connected to it, pistons connected to it, gudgeon pin connected to it. So these are the gudgeon pins. It is going into the cylinder on the lower side. The supports are there. We have a flywheel over here. This is the cylinder head. The cylinder head is going on the upper side of your cylinder block. So the walls are connected to it. The spring is there. Spring retainers are there. The walls are operated by the camshafts. The camshafts are connected. It's in its position. This is the gaskets connected in between the joint. The head is connected to the block. Here the pulley is connected over here. So the drive is given from the crankshaft to camshaft. This is your tappet cover. So the tappet cover covers the tappets or the rocker on the upper side. This is the sump where the oil is going to be there. Here the oil is there in this region. Here the water as the oil pump is there with the filter. And this particular is going to be connected on the lower side. Here you can see the pump and the filter. Now the oil from here will be supplied to the galleries. So this is a part of the different associate accessories connected to the engine. So this is your starter motor connected to the flywheel to start the engine. This is your inlet manifold where the mixture is air fuel mixture is going to supply to the engine. These are the injectors. So to the injector you have the oil pipes, fuel pipes. So from the fuel pump the fuel will be supplied to the injectors. This is this is a water pump. So the water pump is going to here, which supplies the water for cooling system. This is a pulley to drive all these accessories. This is the alternator which generates the power for ignition. This is a supercharger connected to supercharge the engines. This is the exhaust manifold which takes the exhaust gases to the atmosphere. Since it is hot, we have covered it. So this were some of the videos. I think your requirement of some videos, Rishikesh Deshmukh, has been completed. Whatever was supposed to be shown, because basically I have not planned for any videos to be shown. That is why I am not showing all the videos. Let me check out whether I can show any other video which will be of useful. So diesel engine parts. So the injector is over here. Here, sorry. So this is the actual engine working. So how the combustion happens inside the combustion chamber is shown over here. So when the the injection is happening, it is going to burn when the piston is reaching the top dead center. So this is the actual photography of the combustion happening inside a combustion chamber. Okay, these are the walls and these are the manifolds. So the piston is moving, the walls are opening. So there are different types of engines are there, different types of pistons are there. They are being discussed. All these things again we will discuss in one of the coming chapters. I hope the content is up to the mark. Any doubt remaining with respect to this particular points, whatever we have discussed? Any doubt remaining? If not, let us proceed further. Any doubt remaining? Anybody? Anybody having any doubt? Anybody having any doubt? Okay. If anybody is having any doubt, please ask the question. Or I will go for the next point. Some explanation will be required, which I think as a mechanical engineers you should know. So the next point which I'm going to cover, which is out of syllabus, but from the point of view that you are going to be engineers, mechanical engineers, these are very important to be able to understand. So here I've shown just in brief. I'm going to explain. That is why I have used this particular small slide with the much details. So here we are discussing about the different types of cycles. Now you have seen a Otto cycle and a diesel cycle, and here there are three types of cycles shown. One is the air standard cycle, one is a fuel air cycle, one is the actual cycle. Now, can anybody guess whatever the PV diagram for Otto cycle is shown? Will it be a air standard cycle? Will it be a fuel air cycle? Or will it be a actual cycle? Can anybody guess? Am I audible? Am I audible? So can anybody guess the Otto cycle, whatever I have shown? Will it be a air standard cycle? Will it be a fuel air cycle? Or will it be a actual cycle? What it is?
It will be actual cycle.
It will be an actual cycle. Okay. In order to clear this, the concept of this particular answer, to give an answer proper direction, let us discuss what this cycles are. Basically, air standard cycle. Here it is written standard, and it is written as air. So we consider generally air as a ideal gas. Ideal gas. So when everything in a thermodynamic cycle is happening ideally, then it is called as a ideal cycle. Ideal cycle. For example, you might have heard about the Carnot cycle, correct? So Carnot cycle gave the maximum efficiency up to 66% something. Okay, so that was the ideally maximum. And why it is ideal? Because it is assumed that there are so many assumptions being made when we go for discussing the Carnot cycle. What are the assumptions? Assumption is that the gas is ideal gas. Whatever the working fluid is, it is ideal gas. Now, whether the air fuel mixture is ideal gas, answer is no. Second thing, everything is happening. All the processes are happening adiabatically. That is, no heat is being transferred through walls. All the combustion is going to be completed. That is, whatever heat is being added, that is going to be some part is going to be given to the sink, and remaining everything is being converted into work. So there are no losses. So again, ideal thing. Then we assume that all the processes are isentropic in nature, which is not the case. Then again we say it is a complete closed cycle, ideally, which is not again the case, because we have seen that it is an open cycle. Actually, it is an open cycle. So like this, there are so many assumptions made in an ideal cycle, and such a cycle is called as air standard cycle. For example, you have Carnot cycle. Okay, so such a cycle is called as an air standard cycle, where everything is ideal. And in practice, that is, all the processes are reversible. All the processes are reversible means what? When you say reversible process, this process 1 to 2 happens. Then if 2 to 1 happen, then it has to go like the same 2 to 1, like this. And when this will happen, when there is no losses happening during process 1 to 2. But in actual practical, there is no process which are completely reversible. So we have assumed that all the processes are ideally happening. Everything is sorry, the engine is working in a adiabatic manner, that is no heat losses are there, then all the processes are reversible, which is not the actual case. So many such assumptions are there, and therefore whatever we assume to make it ideal, and correspondingly a cycle we design what we call as a air standard cycle. Now, why it is necessary then to study the air standard cycle? When we know that the practical it is not so. Already we know that it is practically not so. We learn air standard cycle because we want to understand what is the maximum attainable efficiency. Certain thing what we want to attain. Obviously, since this is ideal, this will be the maximum. So this air standard efficiency will indicate that these are the maximum things which we can attain. And whenever you have some practical thing, then you will have some gap. Okay, so your actual efficiency will be something different and your ideal efficiency is going to be different. And then once you know the gap, you can find out, or you can put different concepts and try to achieve the maximum possible. Okay, in order to understand that, that is, if a particular cycle is being working, then what is the maximum possible thing which we can attain, considering everything ideal, that will be this much. So cannot say it is 66% around, correct? And that means if you say the thermodynamics efficiency of my engine is 90 degrees, then you will say that no, it is not possible, because Carnot is saying maximum it is 66% possible, not more than that, or 60% possible, not more than that, correct? So you will clearly say that if somebody is claiming that engine efficiency is 90%, he is wrong, because it is not possible. And therefore we should understand what is the maximum possible, and to understand the maximum possible, what you learn is what is air standard cycle. And this particular air standard cycle, when corrected to air fuel mixture characteristics, now here air was the working medium, but now we are talking of air fuel mixture characteristics. That means we have changed the working fluid from air to air fuel mixture, and whatever corrections are needed, then whatever cycle we get will be fuel air cycle. Fuel air cycle. So remember, when air standard cycle, instead of air, we are making the corrections for, instead of air standard fluid, what was we consumed assumed over here was air, but now we are saying instead of air we are using air fuel mixture, and then whatever cycle we have is fuel air cycle. Okay, so name itself indicates there is fuel along with the air in the cycle. So the fuel is going to work as a source of energy. Okay, and such a cycle is your fuel air cycle. And your Otto cycle, diesel cycle, all this particular Ericsson cycle, all these particular cycles comes under the heading fuel air cycles. So the answer for the question was, what initially I asked was the Otto cycle is a fuel air cycle. Okay, now then what is this actual cycle? Now here you can see corrected to different losses. Now this is a theoretical thing. The theoretical cycle, whatever we are getting is this. But theoretical means we are assuming that something is happening, that is the wall is supposed to happen at top dead center, opening at top dead center, but it is not happening. So we have to open it some degrees early. That means your actual cycle is going to be different. Okay, so that is the difference between the fuel air cycle and actual cycle. So the actual cycle is what you get finally, which is giving you the work output, is your actual cycle. Okay, and fuel air cycle, when corrected for different losses, then you will get the actual cycle. Now here it is shown the theoretical cycle and actual cycle PV diagram for Otto cycle. So here 1, 2, this 3, 4 and 1. This is your fuel air cycle, which is indicated by clear different lines. 1, 2, 2, 3, 3, 4, 4, 1. This is your fuel air cycle. But your 1, A, B, C, D and 1. This is your actual cycle. So I hope now why and in the last cycle itself you have mentioned that when the fuel air cycle is connected to different losses, what we get is actual cycle. So you can see over here, this is your actual cycle, and these are the losses. These are the different losses, which is shown by hatched area over here. Okay, and what these losses are? So the losses are, so you can see over here, theoretically you assume that, which we have seen discussed earlier, we assume that the spark is given at top dead center, that is at point 2. But does it we actually give the spark at top dead center? Obviously no. We have to give some degrees before top dead center. That is, we are giving the spark some degrees before top dead center at point A. Now, the theoretical line was 1 to 2, which was supposed to move like this, where there was nothing happening except compression. But since the ignition has happened over here, now the combustion starts. And due to combustion, now the pressure starts increasing along with the pressure due to compression. If the pressure was due to compression, then the line would have like this. But now additional pressure is there due to increase in the pressure due to combustion. And therefore, the line, instead of moving like this, it is moving like this. And by the time piston reaches top dead center, instead of 2, point B is reached. Okay, and still the combustion is not completed. Combustion is not completed. Still the combustion is not completed, and therefore continue the combustion is going to be completed. The combustion is happening, but what happens, since the piston has reached top dead center and it is moving back, the pressure will try to reduce. So the pressure will try to reduce. So theoretically speaking, it should have moved like this. It should have moved like this. But since the piston has started moving from top dead center towards bottom dead center, the pressure starts decreasing. So instead of this line, we get BC line. Instead of B3 dash line, we get BC line. Okay, and at point B, we say the combustion has completed. So theoretical combustion was 2 to 3, but actual combustion line is A, B, C. Okay, so this particular hatched region corresponds to what you call as time loss factor, which indicates around 6% loss. Okay, this is your time loss factor. Why the time loss factor is coming? Because we have given the spark instead of at point 2 some degrees before TDC early, and due to that this particular loss is coming, which we call as time loss factor. So this is your time loss factor, this hatched region and this hatched region. Okay, so theoretically it was from here to here. So this much area and this much area has been decreased, and this particular loss corresponds to around 6 degrees, which we call as time loss factor. So I hope you understood what is time loss factor. So time loss factor is coming into picture due to the loss due to the early spark given in the practical engine. Okay, theoretically it was supposed to be given over here. So your fuel air cycle is 1, 2, 3, 4, 1, but your actual cycle is 1, A, B, C, D, 1. This is your actual cycle. So this unhatched area is your actual cycle, and this is your theoretical cycle. So theoretical cycle means your fuel air cycle, and actual cycle means your final cycle. This will be giving you output. Okay, this will be giving you output, and this is your theoretical thing. So the theoretical thing is here 1, 2, 3, 4, and the actual thing is 1A, B, C, D, 1. Okay, so this was your time loss factor, and the time loss factor was due to the early spark given in the during your combustion. Now, second loss is your heat loss factor. Heat loss factor. Now, what is this heat loss factor? Heat loss factor means we know that we in the actual cycle or even in the theoretical cycle, we don't have any assumption related to heat losses. We are assuming here that no heat is lost. 1, 2 is going to be, so here the instantaneous combustion, this point I have missed. So the instantaneous combustion, when we talked of instantaneous combustion, we got the line 2, 3, but here it is not instantaneous. A, B, C is the actual. So that is why, in other words, we can say the time loss is coming due to the difference between the assumption of instantaneous combustion and actual combustion. Okay. Now coming to the time loss factor, heat loss factor. There are so many heat losses happening due to the different parts of the engine, because you know that the engine is being manufactured with the help of metals. Okay, so many materials which comes under the category of metals, and generally metals are good conductors of heat, and therefore heat is lost. Okay, but we have assumed that there is no heat losses are there. So that is where in the previous cycle, previous slide, we said when we assume the losses, when we consider the losses, whatever we get is your actual cycle. So here the next loss what you are talking of is heat loss. So due to heat loss, you can see over here the maximum point without any considering any heat loss is 3. But actually it is coming to point C. Okay, so if this was moving like this, at least it would have been 3 dash, but it is not so. It is C. Correct. That means this much heat is being lost. So this particular hatched area corresponds to heat loss. So this heat loss is this particular thing. This hatched area is your heat loss factor, and it accounts to around 12% losses. Okay, so the piston is going to conduct the heat, then the combustion chamber is going to conduct the heat, the cylinder wall is going to conduct the heat, some heat is lost to the cooling water. So many heat losses are there, and all this particular heat loss accounts to some amount of energy. And since that much are the losses, and this particular losses are called as the heat losses, and it accounts for around 12% of the energy. So already 6% of the energy was lost due to time losses. Around 12% we are losing due to heat losses. Okay, and now the cycle which was supposed to be theoretically 3, 4 like this, it is coming CD. 3C 4 dash here. Okay, now one more loss is there which we call as the exhaust blowdown losses. Now what is this exhaust blowdown losses? The exhaust blowdown losses are that we know that again when we open the exhaust valve, it is theoretically supposed to be opened at point 4, that is bottom dead center. But are we opening the walls, exhaust valves at or bottom dead center? No, we are opening before bottom dead center. That is somewhere here we are opening. So instead of opening the exhaust valve at 4, we are opening at point D, and therefore instead of moving this line like this, it is moving like this. And this particular hatched region, here you can see this particular hatched region, which accounts for almost 2% of the loss. This is your exhaust blowdown loss. Exhaust blowdown loss. Okay, and when we consider all these particular losses, that is the time loss, the heat loss, and the exhaust blowdown loss, okay, then we get something different, which we call as an actual cycle. Okay, so I hope you understood the different losses. Okay, what are the different losses? The time loss factor, the heat loss factor, and the exhaust blowdown factor. Okay, so this particular are the 3 losses over here, and time loss accounts for 6%, heat loss accounts for 12%, and exhaust blowdown accounts for 2%. Okay, so this is your actual cycle. Actual cycle means this much energy is being made available on the piston. On the piston. Underline the word on the piston. Still we are not talking, but actually where do we get the work output from? From the crankshaft. So we have to again some losses are there. For example, when we discussed about the intake suction stroke, we said the line is moving 0 to 1, 0 to 1. Now here we say 0 to 1 is happening at a pressure. Which pressure? Atmospheric pressure. But just now when we discussed a 2-stroke engine, we have said that in order to air or fuel mixture to move in, we have to generate a negative pressure inside the engine. That means the pressure is not atmospheric. Pressure is lesser than atmospheric. That means 0 line will not be 0, 1 line will not be a horizontal line. How it will be? It will be like this. And in order to make the exhaust to happen, you cannot have the exhaust at atmospheric pressure. If inside the engine it is atmospheric and outside the engine it is also atmospheric, then the gases will not move, because in order to flow to happen, a pressure differential is required. Correct? That means inside the engine you have to be a higher pressure than the outside, which is atmospheric pressure. That means this curve will be something like this. Okay, so the suction curve will be something like this, exhaust curve will be something like this, and this particular, in between this exhaust and suction curve, some area is there, which is again what we call as pumping losses. So that is again another loss, but this loss is not a part of the cycle, because this much work, whatever we have seen now, this 1 D B C D 1, these much work is there on the piston, but as this particular work, also energy moves from the piston to connecting rod, from the connecting rod to the crankshaft, and from the crankshaft to the outside, whatever we are going to take it for an application. In between this, there are again some losses, and this losses corresponds to what you call as a pumping losses, which is there for suction and exhaust. Because in order to suction to happen, crankshaft has to give some energy to piston, and therefore the piston will be moved down. Because see, if the above the piston the negative pressure is there, will the piston move down easily? No, it has to be pulled down. Then and then only a negative pressure will be created. Correct? So that means some energy will be lost. Again, in order to push the gas, some energy has to be exerted on the piston. There again, we are spending some energy. So that means some energy we are spending for suction and exhaust, and that is all. That is what we call as a pumping losses. Okay. So generally, there are 4 types of losses: time losses, heat losses, exhaust blowdown losses, and pumping losses, which is coming in between what you call as the fuel air cycle and actual cycle. So actual cycle, the pumping loss is not included. Actual cycle work minus pumping work is the actual work what you get at the end of the crankshaft. Okay, which I have not written over here. Okay, so I hope you have understood the engine cycle, brief, because this is not a part of your syllabus. But what happens is sometimes examiner tend to ask something. They assume that you being an engineer, you should know something, because already there is written engine cycles word is there, that is the auto cycle and diesel cycle word is there, and therefore this is the basics of this particular cycle, and they may ask it. Okay, though it has not clearly mentioned in the syllabus, and that is why I have cleared this particular words. So 3 types of cycles over here: the air standard cycle, fuel air cycle, and the actual cycle. Okay, the air standard cycle is the ideal thing. When corrected to the corrections for fuel air mixture is made, included, then we get what we get cycle we get is fuel air cycle. And when the corrections are made for the different losses, whatever we have explained now, what we call as the time losses, the heat losses, the exhaust blowdown losses, etc., what we get is the actual cycle. And actual cycle work is being produced at the piston, and in between the piston and the crankshaft, whatever work is lost is called as the pumping losses, and finally we get your actual work output. Okay, so I hope everybody has understood the different losses. Any doubt in these losses, you can unmute yourself and ask. Anybody? Yes. Anybody having any doubt with respect to losses? The 3 losses I have explained. One was your due to time loss factor, that is due to the difference between the instantaneous combustion and actual combustion lines. Okay, that is spark was given early, so that was your time loss factor. Then losses coming due to the heat losses when considered, it is your heat loss factor, which was around 12%. time loss factor was around 6%, and the exhaust wall was opened early. So due to that, some losses were happening, and that was that is what we call as the exhaust blowdown losses. So, and the work spent for suction and compression, suction and exhaust is what you call as the pumping losses. So I hope everybody understood the terms, the different losses like time loss factor or time losses, heat losses, and exhaust blowdown losses. Any doubt? Any doubt? Anybody having any doubt? Please unmute yourself and can ask the question related to losses and the different cycles, the air standard cycle, the fuel air cycle, and the actual cycle. I hope in a short I have made it clear. Everybody understood? Can anybody confirm that you understood? Somebody can confirm that you understood?
Yes, sir.
Okay. If you understood, I will give you the next question. That is your fourth question for your assignment. So please write out the question. Explain the following losses. Following losses. First one, time loss. Second, you have the heat loss. And third, you have exhaust blowdown loss. Exhaust blowdown loss. Explain the following losses. One, the time loss. Second, heat loss, and the exhaust blowdown loss. So this was the fourth question for your assignment. Now I think I can conclude this particular chapter with a last question. Okay. Or instead of giving, can I give some question out of the syllabus? Okay, that I will give in the next lecture. Last one, I will give one out of syllabus question. Okay. So 4 questions for the assignment number 1 has been given. So the first question was related to explain with a neat sketch the PV diagram for a diesel cycle. Then the second question was with a neat sketch explain the timing diagram for a high speed and low speed 4-stroke engine. Third question was with a neat sketch explain the 4 timing diagram for SI and CI engine. And the fourth question was explain the following losses: the time loss, the heat loss, and the exhaust blowdown losses. Okay, so with this, I think I can conclude the chapter number 1, and now the forum is open for doubts. Anybody having any doubt? Please ask any doubt if you are having. If you don't have any doubt, see, whenever I say if you don't have any doubt, you mark your attendance and leave, then suddenly everybody start giving their number and leaving, but nobody is asking the question.
So the loss can be minimized or not? The 6% loss can be minimized?
Can be
minimized or not?
See, minimized or not, that is 6% was the time loss factor. So that is where we have what you call as the spark advance mechanism and retarding mechanism. Okay, so in order to take care of this, what we use is the advance mechanism in the ignition system. So in the ignition system, there will be a system which is going to respond to the speed of the engine. So yesterday we have discussed that whenever the speed increases, we want to increase the time, and therefore we make the spark early. And whenever we decrease the speed of the engine, we have to make the spark late, and for that we try to minimize this particular losses by instead of giving one particular timing. See, if you are using one particular time and if you are not advancing or retarding, then it is going to be lost, because sometimes you have to increase the speed of the engine, sometimes you have to go for decrease the speed of the engine. But if you can accommodate this variation in the speed with respect to spark timing, then it is done with the help of a advanced mechanism, spark advanced mechanism. Okay, and that is a part of a ignition system. So by including a part which we call as a spark advanced mechanism, we try to minimize the losses, that is your time losses. I think I have answered the question. Is it clear?
Yes, sir. Yes.
Okay. Any other question? Any other question? See, as engineers, it is your duty to find out the different ways to minimize this particular losses. Okay. Now the last question I will ask. Last question I will ask, or rather, let that be your last question of your assignment itself. Write down. Explain why two-stroke engines are not used commercially in the automobiles nowadays. Explain why two-stroke engines are not used commercially in the automobiles nowadays. So this is your question number 5. Now you tell me the answer of this. I expect this particular answer from you people. Earlier we used to have this particular please answer. पूर्वीच्या काळात आपण स्कूटर मध्ये किंवा बऱ्याच ऍप्लिकेशन साठी वापरत होतो, परंतु आजकाल वापरत नाही टू स्ट्रोक इंजिन. कारण काय आहे?
Because two-stroke engine produce more pollutions and incompletely burn up fuel. It exhaust.
Correct. Yes. So why that is coming into picture? Why it is coming so? Why it is happening so? असं का होतंय? बरोबर, आन्सर बरोबर आहे, परंतु असं का होतंय? Why pollution is more?
इनलेट वॉल्व एक्झॉस्ट वॉल्व हे 2 स्ट्रोक मध्येच कम्प्लीट होतंय, त्यामुळे स्ट्रक्चर याचं कॉम्प्लिकेटेड आहे, सिंपल नाही.
Okay, so due to the design advantages, due to the design of the two-stroke engine, you can see over here the PPT. I think it is visible. Simultaneously, the transfer port and the exhaust port is going to remain open. And many times, what happens is the unburned mixture, जी काय mixture इथून येणार आहे, fresh mixture leaves out through the exhaust port, and there is unburned hydrocarbons present in the exhaust gases of the two-stroke engines, which is more than the allowable limit due to of today's pollution norms. म्हणजे आजचे नॉर्म्स जी काय आहेत, BS4, BS6 जी काय नॉर्म्स आहेत, त्या नॉर्म्स मध्ये बसत नाहीये. का बसत नाहीये? इथून अनबर्न मिक्सचर डायरेक्टली बाहेर येते. म्हणजे पोल्युशन जास्त आहे, म्हणजे बाकीचं पोल्युशन जास्त नाहीये. Which pollution is more? The pollution corresponding to unburned hydrocarbons. जे काय मिक्सचर मधून अनबर्न्ड येते, फ्युएल वेपर झाले, परंतु ती बर्न होत नाहीये. का? वेळ नाहीये, आणि डायरेक्टली इथं दोन्ही इनलेट आणि एक्झॉस्ट दोन्ही सायमल्टेनियसली चालू असल्यामुळं इथून डायरेक्टली बाहेर येते. अँड देअरफॉर हिअर वी हॅव अनबर्न्ड हायड्रोकार्बन एमिशन्स इन टू स्ट्रोक engines. And nowadays we have very stringent pollution norms, and today's pollution norm does not permit this much unburned hydrocarbon emissions. आणि म्हणून आजचे काल आजकालचे जे टू स्ट्रोक इंजिन्स आहेत ते आजकालचे जे पोल्युशन नॉर्म्स आहेत त्याला पास होऊ शकत नाहीत. दे फेल टू कॉम्प्लाय विथ अँड देअरफॉर nowadays no manufacturer is producing two stroke engine or no manufacturer is using two stroke engines for any vehicles, automobile applications, because all these emission norms are implemented for vehicles. But remember, तुम्ही शेतात यूज करणारे जे फवारणी यंत्र असतं देअर वी यूज टू स्ट्रोक इंजिन, कारण तिथं ती पोल्युशन नॉर्म लागू नाहीये. So we can use the two stroke engine for other applications like for agricultural applications. Okay, we can use it, but for automobile application we cannot use it, because for automobile applications we have nowadays pollution norms and the unburned hydrocarbon which is coming over here. Okay, that is the what is fuel? Fuel is hydrocarbon, isn't it? So the hydrocarbon coming in the form as it is outside along with the exhaust. Why it is coming? Because both the incoming and outgoing is simultaneously happening, and therefore here we have unburned hydrocarbons, and this due to the presence of unburned hydrocarbon in the exhaust gases, which we call as a pollutant. So one of the pollutant is unburned hydrocarbon, and this unburned hydrocarbon is more in case of two stroke engine, and we cannot prevent it. ते आपण completely प्रिव्हेंट करू शकत नाही. का? कारण ही दोन्ही पोर्ट सायमल्टेनियसली कधीतरी ओपन राहणारच आहे. करेक्ट? वी हॅव सीन ओव्हर हियर. आता पिस्टन एकदम खाली गेलं, या पोझिशन मध्ये दोन्ही चालू आहेत. या पोझिशन पासून या पोझिशन पर्यंत याच्यामध्ये दोन्ही चालू आहेत. सो सम अमाउंट ऑफ मिक्सचर इज गोइंग टू एनी हाउ गोइंग आउट, and therefore there will be so much unburned hydrocarbon coming out of the two stroke engine, and due to this we don't have two stroke engines today used in automobile. I hope everybody can answer this question. Yes, somebody confirm me. Point is clear? Yes, somebody confirm. Balaji?
Yes sir,
Confirmed? Okay. Now that time is over, and if any doubt you can ask, otherwise you can mark your attendance and leave. But remember, before marking the attendance, see, we have some sheets over here where I can see very clearly when somebody has joined and when somebody is leaving. And I want Mr. Mane Sujit, Gyaneshwar Thengal and Omkar Saradde to call me at the end after this lecture.
Sir,
after
lecture can you send PPT on the WhatsApp group?
Yes, already I have sent some videos. I have seen that. My video series, I have sent a link. After the last lecture you can check out. परवा दिवसाचे लेक्चर जो होता त्याच्यानंतर तुम्ही जर चेक केलं तर माझी व्हिडिओची लिंक मी पाठवली. ओके, सो यू okay, you see that videos. I think everything is over there. Okay, there are videos itself. So I want Mane Sujit. Mane Sujit is here. Available? Sujit Mane, Omkar Sarade, Gyaneshwar Thengal. Any of this? Others can mark their attendance and can leave.
Okay, bye sir. Thank you.
Thanks a lot. Thanks a lot. Thank you everybody.
हॅलो सर.
हा बोला, कोण बोलतोय?
सुहास बोलतोय. असाइनमेंट कुठे लिहायचे? आपल्या वहीत लिहायचे?
तुमच्याकडे जी काय ट्रिपल पेजेस असतील किंवा जी काय पेजेस असतील त्यातल्या, काय अडचण नाही. आणि
परत कॉलेज सुरू झाल्यावर चेक करायला
ते पेजेस आणून घेऊन यायचे डायरेक्ट तुम्ही माझ्याकडे.
ठीक आहे.
आन्सर्स आता लिहून ठेवा. मी 5 क्वेश्चन्स दिलेले, 5च्या 5 क्वेश्चन तुम्ही त्याचे आन्सर्स लिहून तुमची तयार ठेवा असाइनमेंट.
ओके सर.
हा, कोणाला काही डाऊट असेल तर विचारा, अन्यथा अटेंडन्स मार्क करून तुम्ही लिव्ह करा, जेणेकरून तुम्हाला पुढच्या लेक्चरला तुम्हाला द्यायला वेळ मिळेल. Mane Sujit, Hengal, Omkar Sarade. Any of this is there? Bhupendra is there. Sontake, very good. Okay, anybody having any doubt, please ask. Otherwise, you can mark your attendance and may leave.